And our next speaker is Graham Winter from Diamond Light Source. You've already seen Graham once this meeting, where he was giving an update, but little opinions apparently. And do we get more opinions now, Graham?
You get entirely opinions.
Entirely opinions. All right. So
yes, and some of it is probably a matter of much debate, and I welcome feedback and criticism from the audience.
Marvelous. So again, Graham, I'll give you a wave at 5 minutes.
Yes,
and then
I believe I should be comfortably inside time, but we'll find out. I can't make the clicker work, which is very annoying. Anyway, good morning. Hi. Good, slides are up. So thank you to the organisers for inviting me here. It's great to come and speak at the study weekend. Like everybody, it's fantastic to have everyone here, listen to lots of opinions and drink some beer and talk about stuff. Okay, so some heads up here. First, acknowledgements. So I'm speaking about the wide variety of light sources that we have available. This is basically based on walking around the Earth for the last 20 odd years, going to these sources and asking people stupid questions. So thank you to everybody who has been very patient and tolerant with those stupid questions, explaining stuff to me. I also recommend the technique of learning by asking stupid questions. It's very good. So I would also like to obviously thank Beamline staff for their help and support and so forth with things, and users and people in the audience for asking questions and sharing data and so on. Okay, so fundamentally, we're talking about crystallography. This is still a crystallography conference, largely. We haven't been put out of business by cryo-EM and AI quite yet. Now, in terms of radiation and experiments and so forth, really every source we're talking about is all doing fundamentally the same thing. We have got a tightly collimated beam of radiation. We align a sample with this. We measure some diffraction data. And then we do something to the sample. We either rotate it or we perturb it in some way, or you hit it with a laser or whatever, and then move on and swap it to another one. So fundamentally, even though I'm mostly talking about X-rays, everything I'm talking about here largely applies to everything else as well. And with that in mind, the first thing I would say is universal advice. And I said this yesterday, and I will say this every time I talk. If you are thinking about doing an experiment, talk to instrument scientists, talk to beamline scientists. Most of us are actually really excited by doing crystallography. And often, if you say, I would like to do this thing, many beamline scientists would say, yes, I can do that thing, but actually you might be better off talking to this other person because that's really their area of expertise. So do please talk to people when you're thinking about experiments to do. And the other thing I would say is, if you want to do something really, really crazy, definitely talk to people, because that's interesting and it's fun and it's not the boring day to day. So, you know, we've got people doing acoustic levitation and serial crystallography and in vacuum end stations and all of this. This is interesting. So why am I stood here discussing this? So if you came to the study weekend 10 years ago, then you would have seen many of the same people, all looking a bit younger. At the time, it was all talking about automation and high throughput. And that was really the sort of on the full wave of the structural genomics revolutions and all of this. And you know, actually, that has been incredibly successful. We have filled the PDB up with lots of folds. There's lots of protein structures in there, and people like Elspeth and her students can go through criticizing them all for being radiation damaged. And, you know, it's lots of material out there. And with that material, you've been able to feed it to brain boxes who know about AI and machine learning and linear algebra and stuff. And they've come up with AlphaFold, and that's really good. Does it answer everything? I don't think so. Is it a really useful tool to combine with molecular replacement? I'm almost certain it is. The other thing that's happened probably more 15 years ago, and certainly over the last 10, is the kind of arrival of X-ray free electron lasers. And that has kind of brought about a bit of a renaissance in time-resolved methods. Because, you know, if you go and talk to chemical crystallographers, they've been doing time-resolved crystallography for years. But actually, in our community, it's come more and more interesting in the last decade or so. The last thing which has reappeared or appeared is electron diffraction or micro-ED or 3D ED or whatever branding you choose to use today. So these are things that have changed and are now available to you as users. And I'm going to try and touch on them quickly. So what does this mean? I mean, is crystallography dead? No, it's not dead. It's completely not dead. But it's kind of, your boring rotation crystallography has become boring. It's another tool. It's like you use mass spec or you use everything else. As a biologist, you're just using another tool. So it's means that we as a community have an opportunity to think about other questions. If we're not interested in developing methods for doing static structures anymore, that means we can focus our attention on other things that are perhaps more useful. And personally, and this is an opinion, I think we should be looking more at mechanism. How does this work? And how does this work? We can probe in a lot of different ways. So we can do things like perturbations. And by perturbations, I mean either fragment screening or ligand binding in way of perturbing the structure, or you can hit it with electric fields or lasers and all this other stuff. You know, there's lots of funky stuff happening out there these days. Or you can look at wide populations of crystals. You know, one of the topics that came up yesterday in the panel discussion was actually looking at not just one, this is the kind of gold standard structure for this protein. Let's do lots of them and actually look at the variation between them, because it's probably something to learn. And then lastly, what I'm particularly interested in is this idea of process, of not just looking at resting state at the start and at the end, like you do in ligand binding, but actually how does that ligand bind? How does this molecule react to green light? All these other sorts of questions. And can I capture intermediate time points? And I think that is the thing that is an opportunity that we are presented with now. And I'm just going to try and touch on some of that. So, light sources. I took this map from lightsources.org, which appears to largely be there to highlight who is not a subscriber to lightsources.org. But what you'll see is that there are a number of light sources around the world. They're obviously clustered in places where they can afford to build light sources. So, you know, they are available, and I would encourage people to look at what light sources are available. Obviously, most of the people in this room are from that big clump over there. I won't use a laser pointer, so I don't annoy Harry. But, you know, there are resources available. So if you're thinking about doing some experiments, you obviously have some questions. What sort of experiment shall I do? Is it a serial crystallography? Is it a routine? Is it a fragment screening? Whatever. Which source shall I use? And given a source, which beamline? And to be honest with you, this is for you to figure out. But if you think in terms of what are you trying to achieve with this, what are your samples? How many of them do you have? What kind of information are you looking to get? And where are you? Are all the kind of parameters that you will use in trying to decide how to go about doing the science that you're trying to get done. So if we kick off with routine crystallography, even if you're doing time-resolved studies, even if you're using the new neutron sources we were hearing about yesterday, even if you're using electron diffraction or whatever, it may be worth doing some routine crystallography first to give you a good ground state. And so for this, what I mean by routine these days is taking data from one or more or a few, you know, a countable number of crystals and combining it with a view to getting complete data for structure solution or refinement, but for a static structure. And to be honest with you, every facility represented here and on that map probably is pretty good for doing a sort of static structural biology rotation data collection. Everybody does that pretty well. So to be honest, the best place for you to go is probably your nearest one, or at least the one where you're in the catchment area. So if you're somewhere in the UK, it's probably Diamond. If you're somewhere in France, it's probably ESRF or Soleil or whatever, you know. So it's the geography is probably the principal thing, unless you've got, you know, a good working relationship with somebody else who's doing interesting things in the area where you work. With that in mind, it is still worth talking to the beamline scientists there, because things change. I mean, we were talking yesterday afternoon about the difficulty of engaging with an enormous user community as a facility. How do I put out there this information about things that have changed, new opportunities that have arisen? Well, it's hard, but if you as a scientist go, well, I'm interested in doing this, can you help me with that? Almost certainly you'll get very helpful answers out of any facility you ask. Again, when I said 10 years ago we were focusing a lot on automation, that automation is now part of the mainstream. If the automatic processing stops working at Diamond, my phone rings because people want to know, but what do I do? It's like, you can't tell them, well, you have to process the data by hand, because you can't. You can't handle the throughput. So it's just part of the bedrock. It's like a detector or a goniometer now. So instead of treating it as being like just, you know, either you do or you don't, it's just a tool, use it. Even if you're trying to do a complex phasing experiment, if the beamlines where you're working have automated processing, look at the results. Even if you're processing by hand, it's a second set of eyes, and it's time well spent. And particularly, one of the things, kind of touching on stuff that Amy was talking about just now, if you have lots of crystals, collecting data is now really quick. So collect data from lots of crystals, and then you can either pick the best one, or you can merge some of the best ones, or as Elspeth was saying just now, merging isomorphous crystals and maybe just take a few degrees off each one to get a relatively undamaged data set. It's a good way to go. Now, there are still some variations that we can do moving slightly away from the routine, but still working on regular synchrotron beamlines. So if we think about something like I-23 or was it BL1A at the Photon Factory, these are beamlines built around the idea of doing long wavelength phasing. Now, obviously, long wavelength phasing suddenly became maybe a bit less relevant a few years ago when those brain boxes came up with AlphaFold. But as Kamel was talking about later on, it's still incredibly useful for actually identifying biologically relevant like ions. Is it calcium? Is it magnesium? And so forth. And so that can be very useful. At the other end of the wavelength spectrum, if you're measuring data from small crystals, there's something to be said for using a high energy because you reduce the effective radiation damage from secondary electrons and so forth. So again, it may be worth going to find a beamline that's optimized for that if you've got small crystals. It is still the case that AlphaFold does not solve everything. You may still have to do a phasing experiment. So again, it's worth figuring out where's good to do that and talking to the scientists, because I'm sure they'd still be excited about doing some phasing. Now, one of the things I will say is if you're going to one of these more specialist beamlines, you may not be able to use spine pins. So Anna said yesterday about them having the EM grids to collect data. If you go to I-23, they've got specialist pins. Other facilities have got their own pins. Because if you're doing something that's a long way from the norm, standard pins won't work. So before you think about this, maybe talk to people, find out what tools you need. In terms of the challenges, to be honest, getting good crystals is probably the single biggest challenge in routine crystallography. If you can get good crystals, everything else is nice and easy. If your crystals are grotty, everything else is going to be hard. And there's not really many cases, I think, where if the automatic processing fails, you can get a beautiful data set out of something by doing a bit of manual processing. I mean, maybe you can. I would like to hear about those, but I think it's pretty rare. What I would say is actually almost everywhere has pipelines built around things like XDS and dials for doing automatic processing. Use those. XDS works incredibly nicely on a laptop. Dials works pretty well on your kind of desktop workstation, whatever. The tools are there. They're quite well supported. Wouldn't worry too much. In terms of making the best use, again, really the main thing is either align your sample correctly or collect the data carefully. Try and minimize the effects of radiation damage. Every workshop I ever go to, people say, I've got this really tricky data set. And it's like, and I've made it even trickier by annihilating the crystal in the first 7 degrees of data. It's like, oh, thanks. Can you just not kill it next time? Please, listen to Elspeth. She keeps telling you this. Listen. Anyway, so yes, that is the main limitation, is your sample lifetime. If you are there, then that's fine. If you have a really, really good crystal, and I mean good, I mean awesome, then the other thing to be aware of is actually detectors are not perfect. If you go to YO3 and you put on a really good crystal and you give it all the beams, then firstly, it will only last a couple of seconds, but in that couple of seconds, you'll get loads of overloaded reflections as well. And you can't see that on an IGA. So be aware of the fact that detectors have some limits. Okay, if we move away from X-rays for a moment, use of electrons is becoming more common, certainly more discussed. For that, the samples have to be really, really tiny. So Alistair presented some slides yesterday. If you're using a kind of typical laboratory electron microscope, your crystals need to be under about 100 nanometers in size. Absolutely tiny. I believe there's a fair number of crystals go to EBIC, and then my colleagues at EBIC look at them and go, they're too big, go to VMXM. By tiny, I mean they mean really, really tiny. But on the flip side, you can get complete data out of relatively tiny samples. The scattering angles are very small. I would invite you to actually do a few calculations and figure out the Bragg angles for a 200 keV electron microscope and work out how far away the detector has to be and this kind of thing. It is actually quite surprising. Obviously, high-end microscopes, if I want to buy a synchrotron, it's like, I need £500 million. If I want to buy a high-end microscope, I give Thermo Fisher like a few million quid. They're quite easy to buy. And this is why when you look at the equivalent map I showed just now, there are high-end microscopes everywhere. The flip side of that is if you're building a synchrotron and synchrotron beamlines, you put a lot of tools in place to make it easy to use and helpful for people like the people in the audience. If you're Thermo Fisher, you're building a microscope. It's for doing microscopy. You're abusing it to doing diffraction. So I'm not going to help you at all with that. So there is nothing in there to help you with things like sample tracking and automatic processing and databases and this kind of stuff. So be aware there are some limits. Also, your electrons are measuring the potential inside the crystal. So this is something that has to be handled in refinement, but I believe Phoenix handles that for you. And I presume RefMac does as well. Okay, so best usage of electron microscopes for diffraction is work in progress. I don't think we've got answers for that. Certainly, metadata and image headers is something that we've resolved largely in the X-ray community over the last 20 years. It's not normally a problem. The electron microscopists are all like, here's a TIFF file. It's a picture. And my metadata is in the lab book. So be aware that that's something to consider. I would always recommend you try and process the data as you go, because preferential orientation and so forth is a very likely outcome. And we haven't got much public data on this area, so I think it'd be good if we made some more public. Okay, so going beyond the routine, the first thing I would like to talk about is large numbers of crystals. So this was touched on yesterday afternoon in the XChem presentation, and this is something that's really only become possible because of the investment and effort and so forth that went in over 20 years in terms of automating crystallography, automating the methods, sample delivery, robotics, and all of this kind of stuff. And the idea here is instead of taking, I've got one crystal and I soak it in a fragment, I look at a different density, it's, okay, I've got 600 crystals, I soak them in all sorts of different fragment combinations, and then I use population analysis to look at actually what's going on in here, which bits of the chemistry are common across these fragments, which bits are different, so that we can start doing something a bit more rational in terms of analysis of that data. Now, this is experimentally challenging because handling 600 samples, looping out 600 samples, keeping track of which one's which and all of that kind of bookkeeping nonsense is actually quite hard. So this is not something that you would tackle lightly. That being said, if you're applying for somewhere like XChem, or I believe they do this at Bessie as well, you will be asked tricky questions, as were presented yesterday afternoon, and those tricky questions are to make sure that you can get your science done. They're not there to prevent you from applying for beam time. So I would encourage you to use a specialist center there rather than trying to do it by yourself, because it's going to be very hard. Making best use of that, it's really a case of making sure that you have got really well characterized samples before you go in. Now, the great thing about the application process is they check, have you got really well characterized samples before you go in? And they won't let you go in if you haven't. So it's not too hard, but have a good strategy, understand how the samples behave, because if you're taking data from 600 of them, you want those data sets to be comparable. Okay, last thing I want to touch on is a bit about time evolution. And the main choice we have at the moment for doing time resolved methods is really about serial crystallography at the moment, as far as I'm aware. And for this, at the moment, you've really got one choice of synchrotron or XFEL. Synchrotrons are way more numerous, it's much easier to get time, and it's a lot simpler experimentally. And I'll touch on that in just a moment, but you've got very, there's very big time frames you have to work in, like milliseconds. You can't get much below a millisecond very easily. Whereas XFELs are obviously much brighter. You do get damage-free data. The experiment's a bit more complicated, and I'll touch on that in a second. And it's obviously much harder to get beam time. Now, if you've got synchrotron data, you can use that in the application process for your beam time on an XFEL. And so really the choice depends on the timescale requirements that you have. So if you go to synchrotrons, you've got different sample delivery methods, so fixed targets, sample injectors, tape drives. Obviously, Amy was talking about the use of plates, or you can have the kind of sandwich films and do a massive raster scan and all these other things. There's a bunch of different ways that you can get samples into the beam for serial crystallography. Now, I would say synchrotrons are a really good place to get started with this, because one of the huge advantages you have is a well-characterized beam and a well-characterized detector. So a lot of what my colleagues in Berkeley do is calibration of detectors, because they keep taking them apart and putting them back together again. Nobody ever takes apart the Eiger on I-24, or at least not like without a lot of planning. So we don't have to worry too much about detector calibration. We know what the wavelength spread's like and so forth. But you are limited, even if you go to ID29, you're limited to about 10 microsecond timeframes. So there are some issues there. The challenges, you know, if you've got good samples and sensible settings on the data collections, you can get pretty good hit rates with fixed targets. And the data processing, as was touched on yesterday afternoon and this morning, is pretty well supported. So if you go to sort of I-24 or ID29 at the SRF, you know, there's a lot of tools in place to make it quite straightforward for you to do a serial crystallography experiment. It is not easy by any stretch of imagination, but it's not like the grand challenge that it is of doing a big X-FEL experiment. But I would say it's unlikely you can take the data home on a memory stick and process it on your laptop. Be aware, serial crystallography data are big, and handling those is going to probably involve doing some scripting and learning about a bit of automation. If you go to the free electron lasers, actually a lot of the sample delivery stuff is the same, and I've ripped off some very nice animated GIFs from the Slack web pages here. The advantages you have with a free electron laser is the ability to get to really short time frames. So the exposure times are in femtoseconds. The gaps between your laser pulse and the photons for the X-rays can be completely adjustable. LCLS is running sort of 100 hertz-ish, 200 hertz, thereabouts. LCLS2 is going to be a heck of a lot quicker. But there's a huge disadvantage, and this is something which hasn't, I think, really permeated amongst the sort of wider understanding, is the shot-to-shot pulse variation. So if we look at the average shape of an LCLS pulse, so this was taken from some data from Erin Brewster, if you average a long run of LCLS pulses, if there's 100,000 pulses, you get a really nice pink beam. Okay, so we've got something that's obviously pink, it's got a delta E over E of about 2%. We've got a really nice central energy. If you put your crystals in there, you'd know how they behave. The problem is, this is the average. If you look at any individual images, the actual spectra are completely crazy. And so what's happening here is we have different shots. Every shot is different because it's basically quantum effects giving rise to these the photons, and so there's a lot of chaotic processes. So on average, there's 7,000 and some keV, but you've got quite a spread. And if you imagine for a moment that response function for one reflection is somewhere here with a width of about that much, then how many photons actually activate that reflection can vary enormously from one pulse to another. And to illustrate that, and to highlight one of the reasons why X-FEL data processing is a bit tricky, I've made a really sort of dumb simulation to capture that by multiplying that graph by a simple Gaussian response function, which is kind of a very approximate single dimensional mosaicity model. So if you have a spot with a very wide mosaicity, so it's in reflecting position for a long time, then we've essentially got a big wide Gaussian. This averages a lot of that spectrum. And so we end up with, you know, a fairly well-defined central limit here and a reasonable spread of reflection intensities. Now, this is as good as it will ever get. This is perfect data, completely simulated with only those spectra from Erin. And what you'll see is, even so, quite a few of the reflections come out with no counts. A number of them come out with quite a lot of counts. So, you know, even in that case, there's enormous spread. So you have to take quite a few. But then if we have a crystal with a bit less mosaicity, so 0.1 degree rather than 0.2, say, we end up with a much broader spread, and we start getting a slightly funny shaped response function as well, which I've nicely hidden behind the blue. But what you'll see is some of the reflections are much, much stronger, but there's a really wide spread. And then if we get a crystal with relatively low mosaicity of 0.05 degrees, which room temperature microcrystal, it's quite a plausible outcome, you suddenly have an enormous spread of potential reflection intensities. And, you know, so what you need to do now is take an enormous average to get any kind of true estimate of the underlying IHKL. So this is one of the things I think we've not really touched on much as a community, is how much this wavelength impact affects the intensities that you measure. And this is, I think, a lot of the reason behind why you have to have high multiplicities for X-FEL datasets. So challenges for X-FELs. So this comes back to a little bit to some of this discussion from yesterday afternoon, actually, and I'll get to that in a moment. So the data collection, getting beam time is hard. If you're in the UK and you're trying to get beam time in an X-FEL, I strongly encourage you to get in touch with Alan Orville and the X-FEL Hub team, some of whom are in the audience here, because they will help you with the process of applying for beam time at the LCLS, at Sackler, PAL, other places. Data processing, I would say it is pretty well supported. Everybody working on data processing for XFEL experiments is really committed to the cause and will really try and help you, but it's still hard. And computationally, it's still quite big. The data volume is potentially enormous. So if you do a sample injector experiment with an XFEL, you can take data for like 20 minutes, half an hour at a time at a few hundred frames a second, which doesn't compress very well. You can have enormous amounts of data. If you're doing it with fixed targets, it's a bit more controlled, so I wouldn't worry so much. But yes, there are some challenges there. And this is why when you look at how XFEL experiments work, it's moving more away from the kind of synchrotron visit where you and a postdoc go and collect data for an afternoon, and more towards a kind of particle physics experiment. Okay, where are we going? Well, Diamond have just had somebody written a big check to say, yes, you can have a Diamond too. Woo! So we're about to embark on that quest. APS is just in the middle of that quest. We've got ESRF have been through that quest to upgrade. Everybody is talking about either doing upgrades or they've done upgrades because the technology has moved on a lot. So everyone's getting brighter, smaller beams, higher brilliance, all these other things. It makes lots of crystallography very exciting. Obviously, the detector people, they don't just make a detector and then do nothing for the next 5 years. Yeah, they're developing stuff. So we've got Pilatus 4 coming online at like 2 or 4 kilohertz. We've got Jungfraus that today you can do a couple of kilohertz. There's plenty of talk about 10, 100 kilohertz detectors. I'm not entirely sure how we're going to cope with that. That will be a discovery process. We've got some interesting work going on at Diamond with this thing, which is the Tristan time-resolved detector. So this was built principally for the chemical crystallography community, but instead of taking pictures, it takes events. So every photon, instead of putting that photon into a picture, it just goes, oh, a photon arrived at this timestamp, at this pixel, with this much energy. And you end up with a long list of when these photons arrived with kind of a couple of nanosecond timestamps. So that means you can reconstruct your time-resolved data set at the very end. So this was going to bring us some new challenges. Obviously, the LCLS2 is online in a year or so. We've got Shine talking about a megahertz. Again, I don't know what we as a community will do with a megahertz pulse rate. Not sure. That's going to be an interesting challenge, but that's why we're here, because it's fun, it's challenging, it's not easy. So this is going to bring us some huge challenges with the data handling. And I think this is going to move us again more towards the particle physics world. ED and neutrons, I think, will be very interesting. So I'm going to stop talking now because otherwise Arwen's going to come and tell me to stop talking anyway. And shut up and say, we have got the conference happening not next year, it's this year now, and I've really got to get on with it. But please put these dates in your diary and plan to come to Germany because the GRC is dead. Long live the GRC. It's not the GRC. Instead of it being in Lewiston, it's in Berlin, and it has en-suite accommodation. And with that, I shall say thank you.
Thank you, Graham. Is this on? Yeah, no, thanks, Graham. Despite Sam manfully wielding his bubble gun, we do have time for some questions. Are there questions from the audience?
I have a question from Robert Bosman, who sent me a text instead of using the Slack. So he wants to know how non-standard brackets, so how complicated compared to current XFEL experiments would a serial room temperature electron diffraction data processing be at a 2 to 4 mega EV source, such as LCLS UED?
I have no idea, but it'd be fascinating. If the pulses are well behaved, so you've got an electron gun where the energy distribution is well determined from one pulse to the next, it'll be a hell of a lot easier. The only thing is that you haven't got any curvature. So a lot of what pulls us out of the weeds with processing still shots at the moment is the fact that the Ewald sphere is curved. If you've got 2 MeV electrons, your Ewald sphere is completely flat. And so it's actually quite hard to pin down orientation because you haven't got reflections on this side moving in while the reflections on this side move out because you just got a slice.
Okay, more questions for Graham. I've got a provocative one, Graham. So right at the beginning, you said you can go to your local facility to check your crystal quality. Where do you think home source is? Do we still need home sources, or do we all have a synchrotron close enough?
I mean, I'm certain that there are some home sources out there, and I'm pretty certain if the folk from Rigaku were in the audience, they would give me a bit of a hard time about how bright their new sources are. I don't have one because I've got a synchrotron, so I don't need one. Actually, that's a lie. I used one last summer when I had some summer students. But I mean, yes, for screening crystals, but to be honest, I don't think anybody in this room is doing anything interesting with crystals that are big enough to hit with a lab source these days. You are? Oh, good for you. My crystals are huge, said Arwin.
Anybody else doing stuff?
I'll follow up on this one, Graham. What you're advocating for is doing experiments rather than measurements, right?
Yes.
And but doing experiments comes at the expense that you have to characterize your samples very, very well and know them very, very well. And do we have collectively enough time to actually characterize our samples in a well-rounded manner to actually exploit the abilities we have at all these different sources? Or are we wasting a lot of time actually characterizing them at these high-end sources?
So I suspect you're talking about biophysical characterization and other probes on the time, or actually just measuring
crystals, optimizing crystals.
Oh yeah,
making the
so
best.
I'm kind of taking that as a given that before you apply for XFEL time, that they ask you tricky questions like, have you got decent crystals? I would like to think you have to be able to demonstrate that. Oh, decent crystals that aren't lysozyme. But yeah, I mean, I take it as a given that if you want to get good static structures, that you've already sent them to your local synchrotron or collected data interactively, and you've got good, solid, well-refined ground state structures. If you haven't, then you should do that before you go and do anything exciting and measurement-like.
Good point to finish. We need to move. Oh, go on, Peter, if it's quick.
I was just going to plug the use of a home source again. It gives you the time without the pressure to be able to explore things and also optimize things. So and also it's very hard to learn anything at all when you're at a high pressure synchrotron data collection. So for students, it enables a proper education.
So I may suffer for saying this, but I'm pretty sure if you ask nicely for diamond beam time during the day to bring students down to teach them crystallography, our facilities will be amenable to providing you low pressure beam time for that kind of activity. I may have my colleagues tear me a new one when I get back to the chair. I'll find out.
On that happy note.
Thank you.
Let's thank Graham again, and we'll move on to our final speaker.